Hello everyone, welcome to our talk on static range detection for RTOS applications. I am Rishi Tulsian and this is a joint project with Rekha Pai and Deepak D'Souza. Let's get started with the motivation behind this project. So most embedded systems like drones, heart rate monitors are safety critical applications running on a real-time operating system kernel. Data races in such critical applications can lead to atomicity violations, causing system malfunctions and undesirable behavior. Hence, it is very important to detect data races to ensure safety properties are held and unexpected system behavior can be avoided. Let's consider two threads sharing a count variable. Uh, One thread is incrementing the count variable and the other one is decrementing it. Let's say the initial value of the count variable is 3. So after both the threads complete their executions, the final value will remain 3. Otherwise, if we consider the assembly level instructions for these statements, and we assume that the first thread runs the first instruction, and then it gets preempted by the second thread, which runs all its instructions, and then the first thread runs the remaining instructions. So the final value of the count variable will be 4, which is incorrect. Hence, two high-level statements which seem atomic may actually interfere at assembly level, and this cannot be captured by a classical notion of a data race, which requires conflicting statements to occur simultaneously. Hence, we use a notion of data races by Chopra et al., where if we have two statements S1 and S2 in threads A and B, we add skip statements immediately before and after S1 and S2, and we say that if these blocks can overlap with each other in some execution of the program, then S1 and S2 are in a data race. So let's talk about RTOS applications. These are made up of tasks and ISR threads. There is preemptive priority based scheduling and equal priority tasks execute in a round robin manner. Whenever interrupts are enabled, they are serviced immediately. Let's look at a simple example. The main thread, there are two tasks in the system, A4 and B2. The main thread creates an instance of A4 at a priority 4 with ID T1 and an instance of B2 at a priority 2 with ID T2. And then it starts the scheduler. Since A4 is created at a higher priority, it executes first. It sets the value of X to 0 and then it blocks for 10 time units. When A4 is blocked, B2 executes, uh, but B2 can only execute for 10 units as after 10 units A4 gets ready and preempts B2 as A4 is a higher priority task and the cycle continues. Let's look at another demo application with some synchronization mechanisms. Here we have two tasks, the producer and the consumer, and there are two shared variables in the system, item and count. The main thread creates an instance of the producer and the consumer, both at equal priorities 1. The thread ID for the producer is T1 and that for the consumer is T2. And then the main thread starts the scheduler. Since both the producer and consumer are created at equal priorities, any one of them can run first. When the producer executes, it suspends the consumer before accessing the item and the count variables. Once it is done accessing the item and count variables, it resumes the consumer task. When the consumer task executes, it first accesses the item variable and then it raises its priority to a higher level 2 and then it accesses the count variable. Once it accesses the count variable, it resets its priority back to 1. So we can see that when when uh, when the producer accesses the shared variables item and count, the consumer is suspended and the consumer cannot preempt the producer. Similarly, at line number 23, the consumer is running at a priority 2 and it is the highest priority task in the system, so the producer cannot preempt the consumer at line number 23. However, at line number 21, the consumer runs at a priority 1 and the producer is also at a priority 1 and the producer is not suspended. So at this point, at line number 21, the producer can possibly preempt the consumer. Hence, we can say that the access to item in line number 12 and 21, this can be a potential data race. However, the accesses in line numbers 13 and 23 to the shared count variable, they are race free. So we can see that the producer and consumer use different non-standard synchronization mechanisms, like changing priorities and suspending other tasks. And we have seen um, many instances of these non-standard synchronization mechanisms in Arduino Pilot, which is a CBOS application. Hence we would like to determine these facts that line number 12 and 21 can potentially race with each other. However, line number 13 and 23 are race free. So we would like to determine these facts statically. So we define an occur in between relation between two statements S1 and S2 in threads A and B. We say that skip statements are added immediately before and after S1. And now if S2 can run somewhere after S1's leading skip, but before S1's trailing skip, then S2 can occur in between S1. So quite clearly, if S2 cannot occur in between S1 and S1 cannot occur in between S2, then S1 and S2 are race free. So let's revisit the demo application with this definition of the occur in between relation. So at line numbers 12 and 13, we know that the consumer is suspended. And at line number 23, we know that the priority of the consumer is 2, and which is the highest priority in the system. So we can say that uh, at line numbers 12 and 13, the producer cannot be preempted as the consumer is suspended. And at line number 23, the consumer cannot be preempted since it is the highest priority task in the system. However, at line number 21, neither is the consumer the highest priority task, nor is the producer suspended. So we can see that line 21 cannot occur in between line 12. However, line 12 can occur in between line 21. Similarly, 13 and 23 cannot occur in between each other, and hence 13 and 23 are race free. However, 12 and 21 can be a potential data race. In this example, if at line number 22, the consumer changes the priority of the producer to 3, any statement in the producer uh, could now be run at a priority 3. So unless the line number 22 is executed, any statement in the producer will run at a priority 1, and after line number 22 executes for the first time, or any statement in the producer will run at a priority 3. Hence, all statements in such applications can run at multiple priorities, and hence we use a notion of dynamic priorities where we consider the range of all possible priorities for each statement by denoting the range with the minimum and the maximum priorities. So the goal of the analysis is to is given any conflict pair, can we prove can we prove that each statement in the pair to not occur in between each other and rule them out as race free. So we give 6 sufficient conditions when two statements can be said to not occur in between each other. So the first one is if S1 and S2 are in some tasks A and B, where A suspends B before it does statement S1, and S1 runs at a minimum priority P1, and there is no other task in the system with a maximum priority greater than equal to P1 which can resume P. So in such a case, we can say that S2 cannot occur in between S1. Another case would be when S1 and S2 are in some threads A and B, and the minimum priority of S1 is P1, the maximum priority of S2 is Q2, and P1 is strictly greater than Q2, and there is no other task with a maximum priority greater than equal to P1 which can suspend A. Even in such a case, we can say that S2 cannot occur in between S1. These are four other conditions when we can say that statements S2 cannot occur in between statement S1. Uh, these are more common conditions such as flag-based synchronization, log-based synchronization, enabling disabling interrupts, and suspending the scheduler. So the key idea of the algorithm is to apply these sufficient conditions as far as possible and try to prove if a given conflict pair cannot if the accesses in a given conflict pair cannot occur in between each other, and then we can rule them out to be race free. So the analysis is implemented as a combination of some pre-analysis with the main analysis. The first pre-analysis is a priority analysis, which tries to obtain the minimum and the maximum priority at each statement in a program. Uh, each task is initialized with the creation priority P1. So the pair P1 P1 is added at the first statement in every task. Whenever a task changes its own priority to P5, the input P3 P4 is changed to P5 P5, and whenever a task B changes a task A's priority to P2, a pair P2 P2 is added at all statements in task A. Now from the list P1 P2 P3 P4 P5 P6 etc., the minimum and maximum at each point is obtained by the minimum of P1 P3 P5 and the maximum of P2 P4 P6. So this way we can obtain the minimum and maximum dynamic priorities at each statement in a thread. We use the log set analysis to identify which potential synchronization mechanisms might be in use at a particular statement. So we replace the suspend resume of a task is replaced by a lock and unlock of the same task name. Uh, a lock P is added at the beginning of every task to check for the priority conditions, and for similarly we add corresponding locks for the other four synchronization mechanisms. For any lock or unlock X statement, the transfer function adds or removes X from the set of already acquired locks, and the join operation is the intersection. Once we have the uh, data from the priority analysis and the lock set analysis, uh, we do the main analysis where conflicting accesses are found by scanning for shared global variables with at least one write access. The data from the priority and log set analysis is used to check for if any of the six sufficient conditions can be satisfied for the no occur in between, and if both accesses in the pair can be proved to not occur in between each other, then they are declared to be non-racy. Otherwise, it is declared as a potential data race. This is a block diagram of the implementation where, given an input program, first we do the priority analysis, then we scan for suspend resume information along with the log set analysis and the conflicting accesses generator. We use an alias analysis to resolve pointers to shared global variables. And with all this information, we check for the occur in between conditions. And finally, we generate the list of potential races. So these are some examples illustrating the analysis. So let's say we have two tasks A2 and B2, both of which are created at priorities 2. A2 suspends task B2 before it accesses the shared counter variable and resumes B2 after it's done with the counter access. Task B2 raises its priority to a level 3 before it accesses the shared counter variable and lowers its priority back to 2 after it is done with the counter. So this is replaced by a lock of task B2 and an unlock of task B2, and lock P is added at the beginning of every statement. So we have this information that the minimum and maximum at each point in A2 is 2. The minimum and maximum priorities at each point in A2 are 2, and we hold the lock task B2 at all these points, which signifies that task B2 is suspended at all these points. Similarly, for task B2, we have the information that the minimum and maximum at all these points is 3, and we hold the priority lock. So when we consider these two statements, we see that task B2 is suspended while task A2 accesses the counter. So so task B2's counter access cannot occur in between task A2's counter access. Similarly, since task B2 is at a strictly higher priority than task A2's counter access, task A2's counter access cannot occur in between task B2's counter access. And hence, we declare that task A2's and counter access does not race or is race free with task B2's counter access. If we consider another example where task A1 is created at a priority 1, task B3 is created at a priority 3, and task A1 acquires a mutex before it accesses the shared total variable and releases the uh, mutex M1 after it is done with the access. Task B3 simply accesses the total variable at a higher priority 3. So this is replaced by a lock of the mutex name and an unlock of the mutex name. And we know that the minimum and maximum priorities at all these points are 1. The locks held at all these points are M1. And for B3, the minimum and maximum priorities at all points are 3. So for if we consider B3, we can see that since 3 is strictly greater than 1, task A1's access to total cannot occur in between task B3's access. However, task A1 does not hold any lock or it cannot satisfy any sufficient condition which lets us say that task B3's total access cannot occur in between task A1's total access, and hence we declare these two accesses to be a potential data race. We implemented our analysis using the C intermediate language framework. It is written as an OCaml module in the framework, and we compared an analysis on various benchmarks with previous work by Schwartz et al. And Chopra et al. Uh, the benchmarks we used the are different applications from NXT OSIC, Free RTOS, and Arduino Pilot. So the first 9 programs from bipedrobot.c to counter.c are NXT OSIC demos from which we obtained from Schwartz et al. And dynamic.c and intq.c are free RTOS demo applications. Rangefinder is a piece of code from Arduino Pilot, which is a real-world CBOS application. So this column, conflicting accesses, denotes the total number of conflict pairs found in these programs, and true races denotes the number of conflict accesses which are actual races. We named our tool wrapper, and these metrics denote the performance of our tool. The time taken and the number of conflict accesses declared to be potential races. Percentage eliminated denotes the number of conflict accesses eliminated as race free, and percentage precision denotes the fraction of potential races which are true races. So, on comparison with previous work by Schwartz et al. And Chopra et al., we find that generally our the percentage of races that we can eliminate as race free is higher, and the percentage of potential races which are true is also higher. So we can conclude on the note that most approaches focus on a limited set of mechanisms. Non-standard synchronization mechanisms like suspending other tasks, changing other task priorities, they are not very well studied. But we propose a comprehensive static analysis for detecting races in such RTOS applications, which is sound and efficient. It is widely applicable to a range of interrupt-driven applications that use many specialized synchronization techniques. And in the future, we would like to test the performance of our analysis on other real-world RTOS applications like the Ardu pilot project, which runs on the ChibOS real-time operating system and has a size of about 700,000 lines of code.